A tank has the shape of an inverted circular cone with height 10 meters and base radius 4 meters. It's filled with water up to 8 meters of height. We're supposed to find the work required to empty the tank by pumping all of the water from the top. And they also provide us with the density of water. So let's draw a picture first. So we got 10 meters high, 2 meters in, or actually that's the radius. So I'm going to put 4 meters is what we have here. 4 meters for the radius of the base, and then we got water up to 8 meters high. Let's go set up our axes. I'm going to have the positive direction downwards, and I'm going to have my 0th location at the top, which means at the very bottom x must be equal to 10. And we have water up to 8 meters high, so if 0 is at the top, 10 is in the bottom, this must be x equals 2 for me to give 8 meters of water. Let's go through and look at one representation in the ith interval. So we're in the ith interval, and I'm going to look at the volume of that piece first. And since it's a circular cone, that one little piece is going to be a cylinder, so the volume will be pi r squared h. Now, pi, a constant, the height of this little piece we know as delta x, that's how high it is. And we're going to be in cubic meters since we're in the metric system. The one thing that we have to be careful about is the radius is actually changing, because depending on what representation I pick, let's say I pick this representation, notice that radius is going to be different than this radius. The radius at the top is 4, and as I get lower and lower, the radius keeps changing. Since this is a general representation of one piece of it, I can't call it 4 meters because that's only for the top. It's not consistent throughout. This is a cone, not a cylinder, all the way through having 4 meters for its radius. So I have to come up with a representation for the radius in terms of x, the axis that I've set up. So that's one of the things I have to look at, figure out what r is right here or right there, wherever you choose, in terms of x. So we're going to have to do some similar triangles analysis to figure out what to put in for our radius and then square it. So I've made a triangle out of this cone. I've moved it over to the side to the right. 4 meters on top, 10 meters on the side, and I'm trying to figure out what this radius will be in terms of x. So it looks like I'm going to need to know what this distance is. One way to do this, there's different ways. So I need to know what that distance is, and I'm just going to bring that out to my axis to make my picture clear so I can label that correctly. Notice the segment is not touching my origin or 0th place. That means it's not an x distance, it's some segment dangling out in the air. This is actually xi, wherever location you're at, and this is the rest, the leftover. So for the leftover, what I really have is 10, which was the whole piece, minus this top x piece that touches the origin, gives me the leftover green segment. So I have a 4 up on top, a 10 all the way down, and then the green segment is 10 minus x, and then I have the r that I'm in search of. So now I'm going to apply similar triangles. I'll say 4 is to 10 as this little r is to this 10 minus x. Then I'm going to go ahead and solve for r. So on the left I have 2/5. On the right I have r over 10 minus x. I will go ahead and multiply both sides by 10 minus x. That's going to get rid of this guy, and I end up with r equals 2/5 10 minus x. So we just found our r in terms of the x that we had labeled. And this x, depending on where we're at, that x is going to change, and hence our radius is going to change. So we're going to go and plug this back in there, and our volume will be pi 2/5 10 minus x quantity squared, the whole thing squared, h, which was delta x, that was the height of the cylinder, cubic meters. Simplify that a little bit. We have our volume, cubic meters. Next, we're going to get our mass for that one piece since we have the density of water given to us. So it's going to be, of course, density times volume. We have the volume to be 4/25 pi 10 minus x squared delta x cubic meters times the density of water that they gave us, which is 1,000 kilograms per cubic meters. And notice what happens is our cubic meters are gone and we get our mass for that one piece. So now we have our mass in kilograms. We need to get the force, step 3, acting on that one piece, one representation in the ith interval. And force is equal to ma. We know the mass at the ith location to be what we have above. And also, we know acceleration due to gravity is going to be 9.8 meters per second squared. So now, having simplified things a little bit, multiply those out, this is what we have in kilogram meters per second squared, which we know is really just a force of newtons. So we have our force acting on that one piece. From here, we can get a representation on the work done on that one piece, which is the force times the distance that one piece moves. Well, the force we have from upstairs, the distance is what we need to look at. And we already kind of know that because we talked about this earlier, that that one piece, all the points in that one piece move up to the top. So if I go and look at that segment, here's what I'm looking at. That's my xi. We had already labeled that as our x distance up until the ith location. So we already know the distance moved is xi, and the force we have from the previous step. So we got xi for the distance, and we substitute in our force on that one piece from the previous step. So this we know was in newtons and our distance is in meters, so ultimately we'll have the work on that one piece, newton meters or joules. This will give us the integral, so we're going to go set up the integral next. Okay, let's make sure we made a note of everything. So I have the coefficient here. I have 10 minus x quantity squared. I have an x for my distance and my delta x, which is my dx. Next comes going back to your picture to see where those representations were made based on your axis. So the representations were made from here to here based on your axis. And looking at your axis, it looks like you're doing it from 2 to 10. So your limit is from 2 to 10. So we go ahead and multiply things out. That's a binomial squared. And when I multiply it out, I get a positive quantity x squared and then negative 10x plus 100. And then the x gets distributed through, and from there on you can integrate and plug in the limits, and we get 3362828 joules, or we can put it in scientific notation, approximately 3.412345 times 10 to the 6th joules is the amount of work required to get that water out from the top. So we have the work calculated. Let's go quickly set up our axes a bit differently and see how things change. So if I look at the same cone and set up my axes in the positive direction going up, the bottom would be 0, the very top would be 10, and the water is 8 meters high. Again, if I'm looking at the ith interval, I need to figure out what this radius is going to be in terms of x, because it keeps changing as I go up and down. So now notice I'm pulling out this triangle that I'm making off this cone to the side, 4 by 10. The radius is changing, and I also want to know what this distance is. And if I just pull it out and bring it next to my axis, notice how it touches the origin. So this is really just x sub I or x. It's a distance x depending on how high I am. If I'm here, I may be at 7. If I'm here, I may be at 9. Here I'm at 8, but here I'm just going up x units. So this little distance is x, and I can set up my similar triangle by doing 4 is to 10, this whole distance, as this little r is to this little distance x. Reducing is 2/5 equals r over x multiplied by x, and notice my radius now is 2/5 x. So I go put 2/5 x into my radius. Simplify that, and from there on we're going to get the mass and the force not a whole lot differently than before. So we multiplied the volume from the previous step, what we had here, with the density that was given, 1,000 kilograms per cubic meters. Cubic meters as before went away. And now I have my kilograms, the mass of that one piece. Multiply that by acceleration 9.8 to end up with how many newtons I have as force acting on that one piece. And now I can go get the work done on that one piece. So work on that one piece is the force on that one piece from the previous step times the distance that one piece moves. And this is what I'm focusing on now. So look at this piece. This piece is going to be moved up this distance, and I'm going to bring that back out to my axis. This is the distance that one piece is going to move. And notice that blue segment is not touching my origin. It's going up to 10, so it's the leftover when I take away this x. So 10 minus x is how much this one representation moves up to the top. Again, because the green piece touching my origin is x itself, the whole thing is 10. 10 minus the piece touching the origin leaves me the leftover. That's the distance that that one piece actually moves to go up to the top based on the axis I have. From there, we're going to go ahead and set up our integral. So we got the coefficient, we got x squared, the quantity 10 minus x, and then my delta x is my dx. Now the other important piece is looking at the limits to see, based on my axis, where the water is really contained. Based on my axis, I'm looking at these representations all the way from here, the bottom, to this place right here up here. And if I go back and refer to my axis, I'm looking at it from 0 to 8. So my water is contained between 0 and 8. And I label it accordingly. Notice this integral looks different than the integral we did up here. The limits are different, the distance represented is a little bit different, and so is the radius based on our axis. However, if we go ahead and distribute the x squared, multiply it out, and look at the work done will be exactly the same with this integral as well. It will be 3.4 times 10 to the 6 joules. So it gives you the exact same amount of work done, even though the integral is set up differently.